You unlock this door with the key of imagination. Beyond it is another dimension. A dimension of sound. A dimension of sight. A dimension of mind. You're moving into a land of both shadow and substance, of things and ideas. You've just crossed over into the Twilight Zone.
The ability to contemplate the meaning of the world around us brings out a constant desire to deepen our knowledge and broaden our horizons. This curiosity is fundamental to the development of our species and civilization. From the advent of the wheel to the innovation of engines, from the cultivation of herbs to the development of modern medicine, from the abacus to computers, human history is a record of progress. Our drive to explore has opened the door to new possibilities to improve our quality of life and allow our species to thrive. Throughout the centuries of scientific development, human beings have been driven by the conviction to uncover the mysteries of the universe. But with each new discovery, we were confronted with new questions and challenges. Today, we live in an age in which the possibility of crossing a new threshold of scientific knowledge is within arm's reach. This is the dream of quantum computerization. In 1980, Russian-German mathematician Yuri Minin was the first to propose the idea of quantum computing. A year later, eminent physicist Richard Feynman presented a logical quantum computer model at the Conference on Physics and Computerization. The premise behind Feynman's model rested in the conviction that it would be impossible to conduct the simulation of a quantum system with the use of a classic computer. Feynman understood that the traditional engineering approach to the problem of computer development would never lead to a revolution. He based his reasoning on the laws of nature. Feynman's lectures from the last years of his scientific activities are considered by many to be a key moment in the development of quantum computer theory. Classic computers are devices that, with the use of transistors, process information in the form of sequences of various combinations of zeros and ones, known as computer binary language. In simple terms, a transistor is a type of switch. It can be turned on, which corresponds to binary 1, or it can be turned off, which corresponds to binary 0. The grouping of transistors into special circuits, which are called logic gates, allows the computer to perform calculations and make decisions in accordance with a man-made computer program. The computer's processing power depends on the number of transistors used. According to Moore's law, today this power is doubling every 2 years. As of 2014, the commercially available processor processing the highest number of transistors is the 15-core Xeon Ivy Bridge EX, with over 4.3 billion transistors. In the case of graphic processors, the world's record belongs to NVIDIA, which offers computer accelerators in which the number of transistors exceeds 7 billion. Although this type of device is admirable and undoubtedly contributes to the development of science and technology, it does not change the fact that there are still some problems of higher rank which could not be resolved in optimal time, even by the most advanced classic computers. No conventional solutions or improvements can compare with the endless possibilities offered by the laws of quantum mechanics. The quantum mechanical states of elementary particles, like transistor voltages, can be described in zeros and ones. Depending on the method used, we can apply various kinds of particles to the calculations. Here, the state described by the zeros and the ones is the internal angular momentum of the particle known as its spin. Although it's not possible to describe this particular feature through the use of classical mechanics, it can be likened to a magnetic bar capable of deviations. When the bar is pointed up, the state can be described by a value of 1. However, when it is pointing down, it can be described by the value of 0. In other words, spin up corresponds to the turned on switch, and spin down corresponds to the turned off switch. Using this analogy, we can describe the defined quantum states with the use of binary system, much like a classic computer. However, beyond this point, all similarity ends. The advantage of quantum computing mainly rests in the quantum mechanical feature, thanks which an elementary particle can be in multiple states simultaneously. This type of phenomenon, called superposition, occurs before the measurement that defines the particle's permanent state. Before the measurement, when there's no surrounding noise, the elementary particle experiences superposition, manifesting its quantum ability to occupy multiple particle states at the same time. Thus, in accordance with the principles of quantum physics, a spin of exemplary particle may, in a parallel manner, indicate all directions at the same time, forcing us to describe it with 0 and 1 simultaneously. Thus, unlike the classic computer, where the basic unit of information is 1 bit, expressed by just one number in binary notation, in the case of quantum computing, information is expressed through a quantum bit, i.e., so-called qubit, which is described by both 0 and 1 binary units simultaneously. Working with qubits provides us with incredible new possibilities for the effective processing of databases beyond what we could have ever before imagined. To better illustrate the significant advantage of working with qubits, let's consider the example of all possible combinations of the 2-bit data system. We have 4 possible states: 0, 0, 1, 0, 0, 1, 1, 1. A 2-bit classic computer can at the most simultaneously perform one of these 4 possible functions. In order to check all of them, the computer would have to repeat each operation separately. A 2-qubit quantum computer, due to the phenomenon of superposition, is able to analyze all of these possibilities at the same time in one operation. This is due to the fact that 2 qubits contain information about 4 states, while 2 bits only contain information about 1 state. Thus, a machine with n qubits can be in superposition of the 2 n states at the same time. A 4-qubit computer could analyze 16 parallel states in a single operation. In comparison, a 4-bit classic computer can only analyze 1 state. To achieve the same solution as the quantum computer, the classic computer would have to repeat this operation 16 times. The advantages of quantum computing will continue to increase with the increase in data. It is thus possible that a 500-qubit computer could one day analyze more data than there are atoms in the observable universe. prototypes of quantum computers were comprised of test tubes. Scientists Neil Gershenfeld, Isaac Huang, and Mark Kubinetz made use of the phenomenon of nuclear magnetic resonance to create the first quantum computer model. The model was comprised of a test tube which contained chloroform particles. The apparatus was placed in a constant magnetic field. That helped the scientists to focus on the interactions between the spins of hydrogen and carbon, which acted as a logic gate. The programming was conducted with the use of radio impulses of particular frequencies, which resulted in the variation of spins. The test tube computer model successfully found the element in the 4-element dataset. Although these early experiments were successful, researchers from University of New Mexico claim that these early computer models were nothing more than classic simulations of quantum computing. The possibility of actually developing such a system for practical applications is not readily conceivable. To develop a fully efficient quantum computer, certain requirements must be fulfilled. One of the most important is to create appropriate conditions under which it would be possible to manipulate qubits while allowing them to maintain their unique properties. It is a very difficult task that requires great precision and special equipment, but doing so would give way to a plenitude of possibilities offered by the fundamental laws of nature. However, in a macro world such as ours, there are many obstacles to the development of quantum systems. One of the biggest problems faced by scientists working to develop quantum computers is the issue of decoherence. Each elementary particle is subject to wave-particle duality, meaning that sometimes it behaves like a particle and other times it behaves like a wave. The particle behaving like a wave is subject to a phenomenon known as unitary evolution, which is described by Schrödinger's equation. It's a state in which noise from the surroundings, i.e., decoherence related to, among others, thermal energy is not sufficiently large enough to trigger the leakage of very susceptible quantum information. Such evolution of entanglement and mutual decoherence may be analyzed and controlled in time, which allows for the processing of information in a completely new way. Additionally, it is essential that the qubits remain in the state of quantum entanglement only with each other, forming a coherent system in which the exchange of quantum information may occur between them. Unfortunately, our surroundings are comprised of elementary particles, which only serve to disrupt the precision of quantum processing. Such uncontrolled entanglements of qubits with the surroundings outside the system could lead to a leakage of important information. Consequently, it's essential to isolate and cool the quantum computer processor where the calculations take place. The cooling of the processor to extremely low temperatures, near absolute zero, helps to calm the qubits by propelling them into a state of extremely low energy levels, and as a result, makes them easier to control. Cooling is also important due to the fact that some of the superconducting materials used in the construction of quantum processors and their unique properties can only be used at very low temperatures. Aside from nuclear magnetic resonance, other solutions and phenomena may be used to create a quantum computer, such as polarization of light, Bose-Einstein condensate, quantum dots, ion traps, or fullerenes. Regardless of the method used, the goal is to achieve the capability to control quantum states in such a way that it would be possible to program the computer, perform the calculations, and finally, read the desired result. In 2012, scientists from the University of New South Wales created the first single-atom transistor made of silicon. In light of the many positive and interesting results of the research on the control of quantum states, the team of Australian researchers, led by Michelle Simmons, has garnered worldwide recognition.
You look at it, people want to get computers that work faster and faster. They want to spend less time surfing the internet. They want to solve problems that they just can't do. They want more graphics. So whatever's happening internationally in the world of silicon chips, they are getting smaller every year, and that's actually driven by the market. The market wants things smaller, they want things faster. And it's been theoretically predicted many years ago, if you could make a computer that worked in the quantum regime, you would be able to solve problems you just can't do with classical computers. first of all, you've got to create the single atom device, and the technology to do that just didn't exist 10 years ago. How do you put a single atom in silicon? How do you encapsulate it so it's in a crystalline environment, so it's still within the semiconductor host material? And then how do you actually put wires down to connect to that single atom so that you can control that single atom? To manipulate atoms, you have to be inside a microscope such as the one behind me, and that works in an ultra-high vacuum environment. So it's a big piece of stainless steel with no air, anything inside, so it's a vacuum. And in that vacuum environment, you can manipulate the atoms. And that literally uses a very fine metal tip. And that metal tip, you actually move it across the surface of a crystal. So you see the atoms on the surface, and you literally move that metal tip across, and as it goes over the atom, it deflects. What you're doing is you're measuring a current and keeping it constant. And as it deflects, you're measuring that small change in current as it goes up in height. And so with such a technique, you've been able to image the atoms on the surface. And then by applying pulse voltages to the tip at certain points, you can actually change the chemistry of the surface. And typically what we do on the silicon surface is we take a silicon surface, nice and clean, and we put down one layer of hydrogen atoms. So it just literally has a silicon-hydrogen bond. And then with the STM technique, we can apply a voltage to the tip just above that silicon-hydrogen bond and literally release one hydrogen atom from the surface, leaving a dangling bond. And that's very reactive. And to that reactive dangling bond, we bring in phosphine gas, which will only stick to that dangling bond and nowhere else on the surface. And it's in such a way that we can bring that phosphorus and put it exactly in the one atomic lattice spacing of where we want it. And then once we've done that, we encapsulate with silicon over the top of it. And by encapsulating with silicon, we surround it with silicon atoms. So it's sitting one phosphorus atom, silicon all the way around it. It's a nice clean environment for that phosphorus atom. So here, this is our scanning tunneling microscope on the right-hand side here, and this is connected under ultra-high vacuum with a piece of stainless steel to a molecular beam epitaxy system. I guess it's very few people have, well, actually several groups have tried to connect these two technologies before, and they found that the vibrations from the crystal growth side actually destroyed the imaging that you would get with the STM. So it's actually very difficult to bring those two technologies together. So we actually literally had to work with lots of engineers with both of the companies and independent acoustic engineers to bring the two technologies together. It's a very expensive system. It cost about $3 million. It was one of those turning points, certainly in my career, because if they didn't come together and work, that probably would have been the end of me. We built the whole crystal structure inside the vacuum, one atomic layer by a time. And then at the end, we take it out. And then we have to find it. And that was one of the first challenges we had, was how do we find that single phosphorus atom? And what we've done is, over the last 5 to 10 years, is we've developed techniques and patented them. We're making markers in the surface that are visible all the way through when you put it in vacuum and when you take it out, and making sure that phosphorus atom is registered with respect to that marker. But how do you connect to the outside world? The connections that you've got to make have got to be as small as you can make them, so that when you literally try and address that atom, you're just addressing that atom and not all the atoms around it. So when you take it out, you can see the marker. You put down your metal electrodes on the surface that control the spin states and the electron states of the phosphorus atoms. And then you apply voltages to those on the surface.
The recording of information starts with the introduction of atoms into the lowest energy state through cooling of the device. Phosphorus atoms have electrons which also have a spin. Let's imagine the electron as a pendulum. When it is in its lowest position, it has the lowest amount of energy. But when we start to push it lightly, it gains energy. Such pushes can be performed with the use of microwave radiation, which propels the electron into an increasingly higher energy state. When the pendulum reaches its culminating point, the electron may detach itself from the atom. The single electron transistor is a very sensitive measurer of the flow of electric charge, thanks to which we can examine the flow of a single electron. This type of electron detachment from the atom is equivalent to a particular direction of spin corresponding to the number 1 in binary notation. In other words, our capacity to measure the flow of a charge enables us to learn which spin had a single electron.
So what we see here is first a spin-up electron tunneling in, and then after that a spin-down electron tunneling back out again. To me as a physicist, this is actually the most amazing thing that I've done in my scientific career, to be able to observe something that I would never be able to see with the bare eye, and still we get it visible with these extremely sensitive measurements, to look at one single electron spin instead of things that you can touch with your bare hands.
If the Australian team is successful in increasing the number of qubits such that all of them are appropriately isolated from the environment, while in a state of quantum entanglement, then it will open up a new door in the world of quantum computing. In addition to the universal model based on logic gates, which the Australian scientists have worked on, there are many others. One such model is the adiabatic quantum computer. The adiabatic computer was built by the company D-Wave, which was the first in the world to put such advanced equipment on the commercial market. This company, founded by Vern Brownell and Geordie Rose, began in the Physics and Astronomy Department of the University of British Columbia in Canada, but it later became an independent entity. The idea of building a quantum computer system was born out of the scientists' experiments with superconducting materials. The basic elements of D-Wave's computer processors are called SQUIDs, superconducting quantum interference devices, which are some of the most sensitive devices used to measure the intensity of magnetic field. In simple words, SQUID is a certain kind of superconducting ring divided by what is known as the Josephson junction. The superconducting materials that make up these devices have certain unique properties, thanks to which, at very low temperatures, nearing absolute zero, quantum uniqueness takes precedence over the classic principles of physics that we are accustomed to. For example, in the cooled superconductor, or SQUID, the phenomenon of electrical resistance does not occur at all. And due to a phenomenon known as the Meissner effect, some objects can even levitate. Unlike the single-atom transistor, here, the form of qubit is the direction of movement of many united electrons, which, as a result of the low temperature and superconducting properties, may be considered equivalent to what, in the previous model, was the direction of the spin. In other words, here, zeros and ones describe the direction of flow of electrical current through the superconducting rings. The clockwise flowing current corresponds to 0, while the counterclockwise flowing current corresponds to 1. The entire computerization process in this type of model is based on the probabilistic method of what's known as quantum annealing. Quantum annealing consists of finding the optimal values among all possible solutions. The name of this method is derived from annealing in metallurgy, which is a technique of controlling the temperature of the cooled metal alloy. Slow cooling allows for the formation of ordered crystalline structures. In quantum annealing, the magnetic field is the equivalent of temperature. For instance, to find the lowest valley during a hike in mountainous terrain, we would have to trek across the terrain to finally arrive at the right place. Quantum mechanics reduces this search. Quantum tunneling is a unique phenomenon which allows the particles of the micro-world to cross the walls, contrary to the law of conservation of energy. Thanks to quantum tunneling, the electron searching for the lowest point in the given terrain would not have to cross it up and down, because it would have the ability to penetrate through those intuitive mountains, allowing for much more efficient searches. If the controlled variations in the magnetic field during this walk of electrons are sufficiently slow, then once the magnetic field is turned off, we should be able to arrive at the correct solution, which in this analogy would be the lowest point of the area. D-Wave's first client was an American armaments company called Lockheed Martin, which at the end of 2010 decided to purchase a 128-qubit D-Wave 1 computer for $10 million. In 2013, with the cooperation of Google, NASA, and URSA, D-Wave created a 512-qubit D-Wave 2 computer for an artificial intelligence laboratory. Researchers in this laboratory are using the D-Wave 2 computer to facilitate them in their work on and in areas such as the improvement of voice activation device technology, development of new drugs, climate change modeling, optimization of traffic control, development of robotics, and machine navigation and shape recognition. However, within the scientific community, there is a continuous and lively debate over the question of whether the computers manufactured by this Canadian company can actually be considered as fully quantum. One of the basic allegations posed by the critics is the possible absence of quantum entanglement occurring between the qubits comprising the D-wave processors. However, according to most recent published scientific studies, the computer definition used by D-wave is correct. Only time will tell whether this information is definitive. In order to take advantage of all that is offered by the fundamental laws of nature, we need software and algorithms, which are just as necessary as basic construction elements. Creating the algorithms, however, is a very difficult task, as it requires that we take into account the counterintuitive laws of quantum mechanics. Nevertheless, there are many people who have risen to the challenge. Peter Shor and Love Grover are the creators of some of the most well-known quantum algorithms. Most notably, since its creation, Shor's algorithm has generated a great deal of discussion among the scientific community, as it could be used to break the modern encryption keys, such as RSA. If there were a quantum computer capable of efficiently using Shor's algorithm, the use of encryption, to secure bank accounts and other operations, and the accompanying difficulty of mass numerical division would cease to exist. Classic computers don't handle these type of difficulties very well, so we can sleep peacefully without worrying that our bank account will be cleaned out by a quantum hacker. Another significant algorithm is Grover's algorithm, which was devised to sort through information in unordered databases. Imagine searching through a phone book with a random assortment of names. In order to find a given telephone number, you would have to search through each and every listing, which would undoubtedly be cumbersome and time-consuming. However, by applying Grover's algorithm to a quantum computer, you could retrieve the desired name in only a few seconds. It should be noted, however, that a single outcome obtained from such calculations is only a probable solution. The more times the computer performs the calculations, the more likely it is to find the proper solution to the problem. Quantum computers are devices mainly designed to solve complex problems, which require us to deal with very large amounts of data. These types of machines will soon find their practical application in research laboratories instead of computer games. The role of a quantum computer is to provide assistance in capturing what is beyond the boundary imposed by time and energy needs. Perhaps in the not-so-distant future, we will be able to climb up the ladder to a new rung of possibilities, such as the creation of new drugs, breakthroughs in research on climate change, and the development of new technological devices. It is the hope that these new discoveries will provide us with a deeper understanding of the structure of the reality that surrounds us. And all of this thanks to the laws of nature and the desire to explore, which defines humanity.
space, the final frontier. These are the voyages of the starship Enterprise. Its 5-year mission: to explore strange new worlds, to seek out new life and new civilizations, to boldly go where no man has gone before.